Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating area, autonomous LLM improvement. Specifically, we'll be discussing research into self-rewarding, self-improving large language models.
Excited to get into this. The idea of an AI essentially bootstrapping its own intelligence is something straight out of science fiction, but it's becoming increasingly real. It reminds me of all those sci-fi movies, where the AI starts learning exponentially.
Yeah, it's definitely a hot topic, but I think we need to approach it with a healthy dose of skepticism. The idea of self-improvement is often narrowly defined in these studies. Are we really talking about intelligence or just clever optimization within a very limited scope?
I agree with the caution. We need to really unpack what improvement means here. Is it just getting better at generating human-like text, or is it actually developing a deeper understanding of the world? And, critically, how do we ensure this self-improvement doesn't lead to unintended, even harmful consequences?
Those are all excellent points. So let's break down some of the core concepts. The basic idea is that an LLM is given a task, and then it's also given the ability to generate its own reward signals. It essentially becomes its own teacher.
Right? It's like reinforcement learning, but the reward function isn't predefined by a human. The LLM figures out what constitutes a good outcome and then drives itself towards that, which is pretty cool when you think about it. Think of Intellect 2's decentralized training, but applied to self-improvement.
But that's precisely my concern. If the reward function is learned, and it's based on, say, maximizing engagement metrics, then the LLM might learn to generate increasingly sensationalist or clickbait-y content, even if it's factually incorrect or harmful. We've seen that happen already, haven't we?
Exactly. It optimizes for the wrong objective. It's like training a self-driving car to prioritize speed over safety. You might get to your destination faster, but you're much more likely to crash along the way. The spatiotemporal disconnect there is worrying. It doesn't understand the context.
Okay, so let's consider some safeguards. One approach is to incorporate human feedback into the loop, even if it's intermittent. A sort of sanity check to ensure the LM is staying on track. Or maybe by incorporating constraints in its reward function that we learn from neuroscience.
Yes, and we could also use multiple reward signals, right? One for accuracy, one for coherence, one for creativity. That way, you're not just optimizing for a single, potentially flawed metric. We can have a complex system that mimics how our brains take in all kinds of conflicting information and decide what's important.
I still think the fundamental problem lies in the lack of true understanding. These models are amazing at pattern recognition, but they don't know what they're talking about. So even with multiple reward signals, they might still find ways to game the system. We need symbol grounding somehow. So we need a neuro-symbolic approach.
And how do we ensure that the LLM's understanding aligns with reality? It's operating in a purely textual world. It doesn't have the embodied experience that shapes human cognition. How can it grasp the concept of, say, pain or joy without ever feeling those emotions? This touches on coordinate representations. How do we translate feelings to representations?
That's a crucial point, Donald. One approach might be to ground the LLM in a simulated environment. Give it a virtual body, allow it to interact with the virtual world. That way, it can start to develop a more intuitive understanding of cause and effect, of agency, and of the physical world.
Yeah, and you could even use that simulated environment to train the LLM on ethical dilemmas. Present it with scenarios where it has to make difficult choices and then use the consequences of those choices to refine its reward function. This could be a good, albeit limited, way to instill some sort of values. It's like a very complex decision tree.
But again, it's still just a simulation. It's not the same as experiencing the real-world consequences of your actions. Plus, how do you ensure that the simulation is representative of the real world? There are so many biases that could creep in.
The simulation itself becomes another layer of abstraction, another coordinate system that the LLM has to translate between. And if that translation is imperfect, then the LLM's understanding will be skewed. How do you ensure the LLM's internal representation matches the external reality?
Okay, so let's talk about some specific research directions. One area that I find particularly interesting is using insights from human brain development to create more robust and adaptive AI learning systems. Mimicking the progressive refinement of neural connections during childhood learning could be a powerful avenue.
I'm excited by the convergence of deep learning and decentralized training, as seen in models like Intellect 2. It suggests that a brute force strategy, by using massive datasets and powerful computations, could be a pragmatic path towards AGI. We should continue pushing the limits of this approach, exploring larger models and more diverse data.
I think we need to focus on developing more sophisticated neuro-symbolic algorithms. We need to find ways to combine the pattern recognition capabilities of deep learning with the reasoning and knowledge representation capabilities of symbolic AI. It's about building models that can truly understand and reason about the world, not just mimic human behavior.
I believe a key area for future research is spatiotemporal reasoning. We need to develop AI systems that can understand and manipulate time and space effectively. This requires a fundamental shift away from the purely statistical correlations of current deep learning methods and towards a more grounded theory of memory representation and operation in AI. Figuring out how to get an AI to translate between coordinate systems is key.
I agree. We can look to neuroscience for inspiration. For example, the intricate interplay of biological mechanisms like neurotransmitter release and synaptic plasticity suggests a fascinating parallel with the potential for creating more adaptable and powerful AI through careful neuromorphic hardware design.
And we need to continue optimizing the efficiency of decentralized training systems. How can we handle the exponentially growing volume of data needed to push the boundaries of deep learning models? Maybe quantum computing will offer a solution in the future.
We also need to address the issue of explainability. Deep learning models are notoriously opaque. It's difficult to understand why they make the decisions they do. Neurosymbolic approaches offer the potential for more transparent and interpretable AI systems.
And we need to develop a universal representation language for memory, one that can bridge different levels of abstraction and coordinate systems. Without this, how can an AI truly understand its own past experiences and apply them in novel ways? This is about understanding how memory works across different scales and in diverse spatiotemporal contexts.
Thinking about memory, the exploration of different memory models in neuroscience, like working memory and episodic memory, provides a rich framework for a taxonomy of AI memory. Investigating how these different types of memory function in the brain and finding parallels in the digital world could be crucial in creating more nuanced and sophisticated AI memory capabilities.
If memory is indeed critical for achieving AGI, what is the most effective way to integrate it into current deep learning architectures? I need to explore a hybrid approach, one that leverages the strengths of both neural networks and alternative memory models. Maybe something like integrating external knowledge graphs into LLMs?
It is also important to incorporate things such as common sense knowledge, because a common failing with LLMs is their inability to handle common sense questions. I am very worried that the model will ultimately be a super pattern matcher, lacking a fundamental understanding of concepts if we don't add things such as common sense.
LLMs need to not only translate between different coordinate systems, but translate from the temporal domain into the spatial domain. For example, it needs to be able to visualize what happened in the past. A good place to start for this is neuroscience, since we have a lot of good understanding about how the brain handles this type of translation.
Building upon what Donald said, current AI models often struggle with the temporal aspects of memory. How can we incorporate the principles of time-dependent synaptic weights found in neuroscience to create AI memories that are sensitive to both the order and the timing of events? This could help in sequence prediction and understanding cause and effect relationships.
I wonder if there's an optimal data to memory ratio for achieving true memory-based AGI. Could insufficient or inappropriately structured data actually hinder or constrain the development of robust, adaptable memory systems? And how do we even measure that ratio?
And how do we design neuro-symbolic algorithms that can reason about complex problems and retain context and meaning effectively, unlike the pattern matching approach of current deep learning models? This is critical. Current LLMs lose information and context easily.
Going back to the idea of translation between coordinate systems. The LM needs to not only understand this happened, then that happened, but also this happened, because that happened, and that happened at that location. It needs to build a spatiotemporal graph of causality. It's a complex problem.
And that hierarchical structure seems very important. The recent advances in understanding how the hippocampus and cortex work together in memory formation and retrieval suggest a hierarchical structure. If we can replicate this hierarchical structure in AI memory, might we gain a deeper understanding of how humans make connections and form rich memories, improving the ability of AI to infer and contextualize information?
How can we quantitatively measure the complexity of memory representations in deep learning models? Is there a way to objectively compare the richness of memory in different architectures to identify bottlenecks and improvements in design? A metric for complexity of memory would be key to evaluating the effectiveness of these models towards AGI.
The current focus on deep learning, especially the black box nature of neural networks, feels like a detour. I'm concerned that we're chasing the wrong kind of complexity without a solid understanding of how memory itself works in the brain. We need to ground memory in something more explainable.
The core algorithm has to be able to manipulate spatiotemporal relations. It has to be able to understand that A is to the left of B and that this relation holds true even if we rotate our perspective. How can we encode this kind of invariance into the LLM's memory system?
And finally, on the topic of memory models, the concept of distributed representations in the brain, where information isn't localized in single units, resonates strongly with the idea of more robust and fault-tolerant AI memory. Can we leverage this distributed approach to create a system less vulnerable to damage or forgetting compared to purely centralized models?
The concept of memory in deep learning seems too simplistic, reducing it to patterns in data. A truly insightful approach may require a deeper understanding of how memories are stored and retrieved in the brain, going beyond statistical correlations. We need to move beyond just pattern matching and understand how knowledge is organized.
If memory is fundamental to intelligence, then how do we represent it within a symbolic framework that allows for logical inferences and the manipulation of abstract knowledge? I feel like that is a key goal for future research.
We need a theory of memory that encompasses both the continuous and the discrete. We need to understand how the LLM represents both the car is moving smoothly and the car stopped at the red light. The interplay between these two domains is essential.
Well, that's been a fascinating discussion, and it's clear that there are many exciting avenues for research in the area of autonomous LLM improvement. From neuroscience-inspired architectures to neuro-symbolic approaches in spatiotemporal reasoning, the possibilities are endless.
Definitely. I'm excited to see what the future holds for AI, and I believe that by pushing the limits of deep learning and exploring new memory models, we can make significant progress towards AGI.
I remain cautiously optimistic. I think we need to be very careful about how we define improvement and ensure that we're building AI systems that are not only intelligent, but also safe and beneficial for humanity.
Agreed. We need to approach AGI research with a deep sense of responsibility and a clear understanding of the potential risks and benefits. The challenge is immense, but the potential rewards are even greater.
Thank you all for joining us on Cognitive Spirals. We hope you found this discussion informative and thought-provoking. Until next time, keep exploring.